Okay, so I think it's your midterm week, and we're going to start by reviewing some of the problems from the last section because I don't think that we got to all of them, and I think that some people were still confused by the end of last section. Is that more or less correct? Okay, great. That's what I thought. So I want to do the same L'Hopital's problems that we did last time and see if you remember the techniques that we talked about. And then I have a few maybe more run-of-the-mill L'Hopital problems that you can try out. And then after that, we're going to talk a little bit about methods of integration. And then I think that should be about it. I also want to ask, could I get so A's in the chat means that my problems are generally good. B's in the chat means that they're too hard. And C's in the chat means too easy. Could I get a few of those? And you can private message me if you're embarrassed. Okay, great. Good. So I tried to make them actually a little bit more difficult than usual today, at least the later problems. So let's see how it goes. Okay. So first, I want you to go in your breakout rooms, and I know we did these last time, but I want to make sure that you remember these techniques. So these three problems, and you'll only have a couple of minutes because we did them last time, and I don't want to waste too much time on them. And you can forget A under number 3. So we're going to number 3 on the worksheet, and we're just going to look at B and C because number A is kind of routine. Okay, so breakout rooms, 2 breakout rooms, great. Okay, so for the first one, we want to try and use L'Hopital's rule somehow, but we have no numerator and denominator. So the best way to go about this, in my opinion, is to rewrite it as ln x over 1 over x, limit as x goes to infinity. And then we can take derivatives, and we get 1 over x and minus 1 over x squared. And then we can cross one of these out. We end up with minus x over 1. And so then we end up with, as x goes to 0, we just get 0. Okay?
Sorry, so why do we have to do L'Hopital's for that? Can't we just straight plug it in and we get the same answer?
How plug it in? No, you can't plug it in because if you plug it in, then you get a 0 here, and ln of 0 is undefined.
I thought ln of 0 was 1.
No, so e to the 0 is equal to 1. But remember, ln of 0 is asking e to the x is equal to 0. What is x? Right? So there's no solution to this. It's minus. It goes towards minus infinity.
All right.
Yeah. Good question. Okay. So for the second one, we also want to try and use L'Hopital's rule somehow. So, but again, we don't have a fraction. So what are we going to do? So let's say that L is equal to lim x goes to infinity x to the 1 over x. Then we have that natural log of L is equal to natural log of lim x goes to infinity x to the 1 over x. And I think you talked about in class how you can flip these two. And then you get ln L is equal to lim x goes to infinity ln x to the 1 over x. Then we can use a log rule. the log rule gets us lim L is equal to lim x goes to infinity ln x over x. And then now you can apply L'Hopital's rule, and you get that this is the same as lim x goes to infinity 1 over x and 1. And so that goes to 0. And so if ln L is equal to 0, then we can exponentiate both sides, and we get L is equal to 1. Okay? Cool. So these are two very valuable techniques that could come up a lot. The other L'Hopital's rule problems in this section are still good problems, but I think they're fairly mundane. So I maybe won't go over those right now. Let me move on to U substitution, okay? So, oh, no, be quiet. So the idea here behind U substitution is that you have some sort of integral that you're evaluating. So your integral will look like, come on. Yeah, so you have some sort of integral that you're evaluating that's of the form like f g of x d g of x, okay? And so the idea here is, instead of integrating over x, which may be really convoluted because it's inside a nested function or something, now what you're going to do is you'll do f of u, and you'll replace dg with du, okay? Does this make sense? Have you seen this before, or am I just talking nonsense to you?
Wait, sorry, what's the dg of x?
So the idea is, when you get a function that's of this form, where you end up with an f in the outer function and you're taking some sort of integral, right? And there's a dx here. Then if you happen to notice that your integral is of this form for some g, then instead of integrating over the normal variable that you want to integrate over x, it helps to instead integrate over g of x. And what we do is we call this g of x u, okay? So let me give you an example. So say that you have cosine of x squared, okay? dx. So a problem is, oh, sorry, I need a 2x dx. So I don't really know how to integrate cosine of x squared on its own, right? Because it's, some nested function that's not very pleasant. But what you can do is you can rename x squared u, and then you can note that 2x is the same as du, okay? So then what you can do, or if you prefer, du dx, okay? And so then you have a dx here, and you can cancel these, and you get u du. So then you can integrate over u instead of x, okay? Have I lost you?
Is this integration by parts or just normal U sub?
No, this is normal U substitution. So the idea here is you do cosine of u, and then this is du, and then once you integrate this, you end up, of course, with you end up with sine of u. And then all you have to do is you just plug back in your x squared for u, and then you get sine of x squared. Okay? Oh, and then if you care, plus c. Okay, so does this make sense? Are there questions? Okay, I like affirmation, so if I can get some after I explain, that would be good. Otherwise, I don't know if anyone understood. Okay, yeah, so you wish every U sub problem were this easy. Well, it's okay. We'll do some harder examples now. And then we'll do some trig sub, which is even harder. So if you have, why don't you try the following two problems, which are also on my worksheet. They're number 4, parts B and C. So that's the first one. And the second one is 1 minus x squared x dx. Okay, so go and try these two, okay? Let me put you in your breakout rooms. So yeah, don't worry, they'll get worse, I promise. Okay, so is the inner function. So w, yeah, the u here is the inner function, which is w minus ln w, and its derivative is just 1 minus 1 over w. And so that means you can do cosine of u du, and that gives you sine of u plus c. And then you plug in for u and you get sine of w minus ln w. And then of course there's the plus c. So the second one is also a u sub. And in this case, the u, so you can do this by trig sub, but you can also do it by u sub. So you can make the u equal to this inner function. And then the derivative is minus 2x of u. And so then you end up with square root of u du divided by minus 2, right? Because you don't have a minus 2 here. So you just have to modify the differential part a little bit. So then you end up with, everyone knows how to integrate this. This is u to the 1/2 over minus 2 du. And that gives you u to the 3 over 2 times 2/3 over minus 2 du. Oh, sorry, no more du, plus c. And then all you have to do is plug back in your expression for u, and you get 1 minus x squared 3 over 2. And then these things cancel, so you get minus 1/3 plus c. Is everyone happy with this? Great. Okay, so now let me talk a little bit about trig substitution. Trig substitution is very similar to u substitution, except this time, instead of replacing an expression with that's a function of x, generally you just replace x itself with a trig function, okay? And so there are a few caveats here. Like if you have a function f of x and x is going, so say that x is being integrated from like 0 to 10, then you really can't replace x with something like cosine x or cosine u, right? Because if you replace x by a cosine u, the range is wrong. So you want to integrate this function from 0 to 10, but cosine u goes from -1 to 1. So if you try and integrate this thing to 10, it's going to be a disaster for you. So you have to choose your trig functions very carefully. So the first example that I have for you is straightforward. So I'll do this one, and then the first one on the worksheet is basically the same as this one, and the other two are both really hard. So if you have 1 minus x squared dx integrated from 0 to 1, So what you can do is you can plug in cosine u for x, okay? And then you get 1 minus cosine squared u, and then du is minus sine of u. And then this time, because you're integrating cosine from 0 to 1, you're going to want to integrate from, I think, so cosine is 0 at pi over 2 or minus 3 pi over 2. So we want to go from 0 to 1. So let's say minus pi over 2. Let's say minus pi over 2 to 0. Okay, so does this choice make sense? Because on the unit circle, we want to integrate, we want to integrate from cosine is 0 over here up to cosine is 1. So we're just going to move along the circle there. Okay, so then what we can do here is we get sine of u under here, because would it be du divided by sine of u? No, not in this case. The reason being that in this instance, it's not the same as u sub, okay? Because you're not replacing an expression of x with something else. You're replacing x itself with a different variable that's easier to integrate but has the same domain, okay? Yeah, so, oh no. So here we're going to get sine u and another sine u, and then we have a du here, okay? Right, so then, and this is just because dx is now d of sine u, and so this is the same as d sine u, and then dx, because u is basically subbing, or sorry, du, d of sine x du, and this is chain rule. So, sorry, it was cosine. So here we have the derivative of cosine of u. So the derivative of cosine of u is just going to look like d cosine of u, which is just sine of u, and then you'll have a du outside because you're now integrating over u, okay? Does this make sense, or did I lose people?
Yeah, sorry, I don't get how that relates to what we have with the sine squared of u.
Oh, so I'm just saying you need a du now because you're integrating over du. Oh, over u, right?
Okay.
And I was trying to motivate why you might see that. But anyway, you can forget it and just remember that you need a du if you want. So, okay, we're going from minus pi over 2 to 0. And so now we just have to integrate sine squared of u, okay? So have you guys seen the lowering powers formula yet?
Doesn't ring a
I
bell.
think so.
Okay, so have you seen trig sub yet?
We did some stuff with it yesterday, but I was so confused.
Okay, hopefully this is helping. So yeah, trig sub is very confusing. So let me step back a second then and talk about lowering powers formula. Okay, so then we'll come back to this problem because otherwise it won't make a ton of sense. So when you're doing integrals in terms of trig functions, there are a few extremely important rules that you should remember or know how to derive. So one of them is the double angle formula. So this says that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. Okay, and why is this useful? Well, you can imagine a situation where you'd have to do something like integrate cosine squared u minus, or cosine squared theta minus sine squared theta, right? So then what would you do?
Is that a trig identity?
Yes, these are important trig identities. So what you do is you could rewrite this part as cosine 2 theta d theta, and then you'd end up with, so the integral, you know how to integrate this now using normal trig sub, right? So then you could do sine 2 theta over 2 plus c, right? Just by doing a trig sub of u is equal to 2 theta, okay? Okay, so I'm trying to pause, but just shout if you're confused as well. So another important one is sine 2 theta is equal to 2 sine theta cosine theta, okay? And more generally, if you have sine a plus b, it's equal to sine a cosine b. Oh boy, am I forgetting my trig identities? So this is equal to sine a cosine b plus plus sine b cosine a, okay? And again, you can imagine why this would be useful. It's because if you had something like sine ax plus bx that you're integrating, again, that's right. You should follow that link to Paul's online math notes. Yeah, thanks. So something like this, or something rather like this, where you have something like sine ax cosine bx plus sine bx cosine ax, and you're integrating over x. So if you have something like this, I don't know what to do with that, but I do know what to do with sine ax plus bx, because here you can rewrite it as sine a plus b x, and then that's easy to integrate, right? Okay, so let me also tell you the lowering powers formulas, because they're also extremely important. So if you have something like cosine squared of theta and you want to integrate it, I don't know what to do with this, because there's no easy trig sub that I can see, and there's no way to do a u substitution that I can think of. So then what you're going to want to do is use this formula. So cosine squared theta is equal to 1 plus cosine 2 theta over 2, and sine squared theta is equal to 1 minus sine 2 theta, 1 minus cosine 2 theta over 2, okay? And generally, I'm not a big fan of memorizing formulas, but I think in this particular case, these are two formulas that you should really know, because they'll come up a lot, and sometimes you'll see some power like this and you're very close to solving an integral, and if you don't know how to lower the powers on the integral, then it's over for you. You're not going to know what to do. Because a lot of tricks, if you don't know them, there's a workaround, but this one, there aren't simple workarounds that I know, okay? So then you can rewrite this as 1 plus cosine 2 theta over 2, and there are d thetas on all of these, of course. And then that gives you, you know how to integrate this. This just gives you theta over 2 plus sine 2 theta over 4 plus c, okay? And if that was too fast, you can go through it, in the privacy of your own home. and look carefully at why this last step is true. And then there's one more formula that I want to tell you, which is sine squared theta d theta, if we integrate this, is equal to I guess I gave you the formula. So then you'd want to do this, right? And then you can use the same method. And the only difference is that the plus would turn into a minus in this case, okay? Okay. Cool. So let me go back to the problem that I was talking about. Where was it? Where was it? Oh, here. Right. So then you end up with a sine squared u. And so now you actually know what to do. So if you have sine squared u, you can rewrite it as 1 minus cosine 2u over 2. You integrate from minus pi over 2 to 0 du. And then, oh, sorry about the board management, but you end up getting, so u over 2, and then we want to integrate cosine, so that gives you minus sine 2u over 4. And then we're going from 0 to pi, or minus pi over 2 to 0. And that gives you, so the first one just gives you 0, because you put in a 0 here and a 0 here, and those collapse down to 0. And then for the second part, you're subtracting minus negative pi over 2 divided by 2 minus, so sine, so you plug in minus pi over 2 for u, and you get sine minus pi over 4. And then that just gives you pi over 4, okay? So hopefully I didn't make a mistake, but does that seem reasonable to people? Not really reasonable. Oh, well, that's unfortunate. So let me ask you to do something quickly, because we don't have a lot of time, and I realize that if this is challenging, then the next two are going to be impossible for you. So why don't you try, but the idea of, okay, it looks daunting, but it's going to become natural the more you do it, okay? So it's daunting to everyone at first, but you just have to do a lot of repetition, and eventually you just start seeing these things, okay? So this time, I want people to try this integral, 1 minus x squared. And let me modify it slightly. So this time I want you to try and do this one, okay? And we'll just go from 0 to 1 again. And I guess we can do breakout rooms. Over it. So you end up with, I told you to substitute in cosine theta over 2 for x. So then you get 1 minus 4 cosine squared theta over 4 square root, and then your derivative here is minus sine theta over 2 from 0 to 1, or again, it'll be from minus pi over 2 to 0 d theta. And so then you end up with 1 minus cosine squared theta square root from minus pi over 2 to 0, and then minus sine theta over 2 d theta. And so that gives you 1, so sine theta, because 1 minus cosine squared theta gives you sine theta. So you get sine theta minus sine squared theta over 2 d theta. And then you're going from minus pi over 2 to 0. So that gives you 1 minus cosine 2 theta over 4. And of course, you have your minus sign here from 0, or from minus pi over 2 to 0. And that gives you, so plug in. Wait. Also, I think on the last one, I may have, oh no, I'm fine. So then you get sine squared. Yeah, so then we're integrating. Sorry, I forgot the integration step. So then we're integrating this thing, and this gives us minus theta over 4 plus sine 2 theta over 8, and then you go from 0 and, oh no, sorry, I'm out of room, pi over 2. Okay, so does this make sense to people? Did people come up with this? Great. Oh, okay, so that's about our time for today. And so you may or may not notice that on CCLE, I posted office hours, which are Tuesdays from 11 until noon, and Thursdays from noon onwards, noon until 1, okay? So yeah, thanks for showing up to section. Hopefully this was helpful. And good luck with your midterm if that's coming up.